Welcome to this new episode of Crop TV. In this talk, I'd like to share you some research results and some suggestions concerning the performance of in-field management practices at reducing dissolved phosphorus loss from corn-soybean rotation. That's what with the system that we did the research on. See, when we talk about phosphorus loss from fields, we can analyze and classify the phosphorus in the runoff in many different ways. One is dissolved phosphorus. This has the larger impact, and the sooner impact is almost immediate on algae growth, but often has short-term effects. It's most of the P, almost 99% in subsurface drainage, and it's a very, very variable proportion in surface runoff. Then we have the particulate P, or sediment-bound P to soil particles. This has a slow but long-term impact on water quality. Now, it has a very variable effect depending on many conditions, including the lakes or streams' depth, the distance that sediment is transported to, and so forth. The Iowa P index considers both particulate P and dissolved P. The particulate P is in the erosion factor of the index, and the dissolved P is in both the surface runoff and the subsurface drainage factors. Now, the total P reduction is considered by the Iowa nutrient reduction strategy. It is very important to consider the ways that phosphorus moves off fields, because if you have a flat field, no tile drainage, no slope, then that phosphorus will not go anywhere likely. It could go some dissolved P deeper into the groundwater, but normally the main problem is with surface runoff. So this picture kind of shows all the different ways that the phosphorus can leave fields. And I'm not going to go through each of one, but essentially we have losses with soil erosion, with surface runoff, and then subsurface drainage that we usually think of tiles, but also happen if we have coarse texture soil or subsoil. And then we have, of course, sometimes the cows doing their things, or the geese in the streams or the lakes. So there are many, many, many factors to consider. One issue that is confusing is because there is no general agreement about how this dissolved P of the most active P in the runoff is measured. So I put this slide just to define some things. The most commonly used fraction of dissolved P in runoff is the dissolved reacted P. That is measured after filtering with a very fine filter, and is measured with a standard colorimetric method, which is the Murphy and Riley method. Then we have total dissolved P, because especially research over the last 5-10 years show that there is sometimes much dissolved P there that the dissolved reacted P doesn't measure, because that colorimetric method measures only orthophosphate. But there could be other forms of phosphorus labeled inorganic or organic that then when we digest this filtered extract, we then measure more P. That can be digested or can be measured with a ICP. I'm not going to go in details, but the ICP measures everything there in the extracted solution, not just orthophosphate P. Then we have bioavailable P, which the most common method is what we call the filter paper coated with iron oxide. And this is a long shaking, with runoff, with paper coated with iron oxide that absorbs the phosphorus and then is removed, and measured. And usually it's measured with colorimetric method. It's long pain in the neck method, and it's not very commonly done. Supposedly, it measures not just the salt P, but all the P that is rapidly available for algae. And then we have total P that is measured by a strong digestion. There are several methods. And then in this case, it doesn't matter if it is measured with a colorimetric or ICP because everything is digested. Some people are beginning to use, especially over the last 2-3 years, the term total reactive P. This is because they don't. It's mainly used for drainage, for tile drainage, because they don't filter the sample through that very fine filter, because normally there is not much sediment there. It's a clear solution. So then they use the colorimetric method, the Murphy and Riley, directly without filtering first. And who knows what that measures, because there could be some forms there, the phosphorus that is being measured, but it's kind of confusing. So I will be talking mostly about the ERP, total dissolved P, or total P, okay? Before we start showing the impact of the practices, I just put this slide because we have an idea already what are the phosphorus management practices for crops that can be good for the environment in terms of minimizing losses of phosphorus with runoff, but there are others that are not so nice for the environment. So we need to know the optimal soil test values and the application rates for the efficient soils. The problem with this is that the rates that we provide, sometimes people use in different ways. Often they want to build up the soil test P faster than the gradual increase that we get with recommended rates. So they apply the phosphorus at once for 2, 3, or more years, which of course that is not good for the economics of the farmers, but also increase the risk of losses. We also have to know the average yield and removal with harvest, because this is used normally to maintain soil test values, the removal-based rates. Then, of course, there is large within-field variation of soil test yield and removal, and I have been for long an advocate of good dense soil sampling, use of yield monitors, and variable rate technology, because the vast majority of the fields in Iowa test optimal high or very high in P, and they keep applying a removal-based rate. So with variable rate technology, they can stop applying to some high testing areas. And then the use of manure. That's an issue because when the manure is applied N-based, based on the nitrogen needed for corn, in some systems it could be a major problem because build up phosphorus a lot, and that's why they should be using the phosphorus index there too. So, and the problem is mailing continuous corn with all manures, because here we have the annual applications of manure, and then of course the phosphorus, just build up very fast. Then in corn soybean rotations, soil manure is not a big problem because normally the amount of nitrogen applied for the corn implies that the phosphorus applied is sufficient for the next crop. And but there is a very large buildup with poultry manure because of the high nitrogen-phosphorus ratio and lower available nitrogen than in soy manure, and also in beef or dairy manures, maybe because also they have lower available nitrogen, and the amount, the concentrations are extremely variable. So and the ratios, depending on the diet. Okay, this is something that we did long ago. Essentially, the two charts shows the relationship between dissolved reactive P, dissolved phosphorus in runoff, with, in this case, I just put the Bray soil test phosphorus method, and but I've done this with all the methods that we support in Iowa, the Melic and others. So we see that the phosphorus soil testing increases, there is essentially a linear increase in the loss. Now, the relationship is much better when we have a shallow sampling depth of 2 inches. The figure on the right shows that we have the normal 6-6 sampling rate, and the correlation is not so good. But in general, that's what happened. Now, if you look at these 2 graphs, you will see the very high numbers. I had to work hard to find in Iowa soil tests over 300, 400 parts per million, and in some of those, I had to create them. I had to put very high rates in advance. And so if you look at the scale, of the soil test, you will see that from about 0 to about 40, 50 parts per million, essentially there is no good relationship, you see. Really, the impact of high soil test phosphorus start to really be clear from the background noise when you have about 40 ppm, 30, 40 ppm or higher than that, okay? Then this is a graph that it may be difficult to understand, but I wanted to show how the soil test P level influences the proportion of the soil P of the total runoff P. So in the graph at the left, we have the ratio total P divided by the DRP concentration, and you see that by the soil water extractable P, which really measures the very available and soluble P in the water. On the right, we have the same thing, but for the MELIC3 test. And you can see there that until about 10 ppm of the water extractable P and about 50 ppm of the MELIC3, essentially we can have, from the proportion of the soil P can be extremely low to very high there. But once we go up those levels, when we have really high testing soils, the ratio comes really down because at those very high soil test levels, the vast majority of the phosphorus that comes out is the soil P. So that's one of the problems. As the soil test P increases over about, say, 40, 50 parts per million, then the amount of phosphorus that comes out is mostly soil P. I can explain that, but I don't have time to explain it here. But this is what happened. Then, of course, the impact of rate. These are averages across several field trials under natural rainfall and simulated rainfall. In most of these trials, we have just 0, 50 pounds, and 100. It's very expensive to have many rates when we are looking at losses with runoff, and most of the time we can do only that with rainfall simulations. But 50 pounds is about the maintenance rate for corn soybean rotations in Iowa. So we can see on the chart of the left that that's the dissolved P, and in the middle is the particular P, and then on the right, the blue is the total P. Note the different scales of the y-axis in these 3 graphs. So we see that when we apply these 50 pounds, there is really, it's a little bit more than with the control, but there is very little phosphorus coming out. And this happens especially when there is no rainfall, no runoff immediately after the application. But then when we put a higher rate, a 100 pound is about double the rate, the annual maintenance rate, and it's commonly used for people that apply only once the phosphorus rate for the corn soybean rotation for maintenance. That's about 100, 120 pounds. So there is an increase. And then we see clearly that as the rate increase, then the amount, the proportion of the dissolved P increases. Okay. Now, one issue that long has called attention of research, in other states and here, and there has not been much research because it's very difficult to do placement research. Rainfall simulations are not that good for placement in the field, and so we need the field studies, and they're expensive, and we cannot use different rates and so forth. So in Iowa, we were lucky that we have two major studies. One was from 2013 to 2018, and this study was on one site. We have 6 years corn-soybean rotations. We have no till and tillage. We did the most common tillage system for each crop in Iowa, and then we broadcasted. It's only broadcast the 2-year rate once before corn in the fall, okay? And also planter band each year. So we are confounding here. You see the timing and the rate, but this is what most people do, either broadcast a 2 rate before corn, and some people in addition, or instead they put the phosphorus with the planter each year. The other was a study that was planned to be at least for a year, but it was cut. The Nutrient Center cut the funding. We have only 3 years. It was only no-till, and it was focused on study better the impact of the rate and the time of application. That in the previous study, it was confounded. So in this case, we have 6 treatments that I listed them there. Essentially, we have broadcast the annual maintenance P in the fall or in the spring, okay? That we didn't have before. We have the planter band annual maintenance for each crop in the spring. Then we have broadcast twice the P maintenance, but only before corn, okay, every other year, or only before soybean. We never have studied this before. And then we have also this broadcast twice phosphorus maintenance only before corn, but using a rye cover crop for both crops. So the results of the first 6 years of the study were a bit surprising. Now, this was consistent in all the years, and we have here in the chart at the left, we have the total P, okay? In the middle one, we have the particulate P, the sediment-bound P, and in the right one, we have the dissolved P, dissolved reacted P. And as you can see with the different color bars, the black is bonding with tillage. The gray is broadcast with tillage. The dark blue is bonded with no-till, and the light blue is broadcast with no-till, okay? So we see essentially one major difference in the total P and in the particular P. The highest losses are with chisel and broadcast. Now, we applied this in the fall, remember? And there were essentially not much difference between the other systems. Now, when we go to the right, and we look at the dissolved P loss, we see that the lowest dissolved P losses are with binding, planter binding with chisel plow tillage, okay? And there is no differences between the other 3 systems. So this notion that by applying the P in the subsurface, and the surface of the soil with placement that can reduce phosphorus losses a lot, this is, it may or may not, you see. These are 6 years of data, a very precise study. And what we conclude there is that really the placement apparently is important when there is tillage and lots of soil, and phosphorus loss because of the tillage. That is not what we expected. Most people expect that to be the case in no-till. But this is what we found. In the second study, and I know this is a complicated chart, but you guys have time you can stop the presentation and look at it carefully. We have a total P on the left, total dissolved P in the center. You see, in this study we measured total dissolved P too, and then the dissolved reacted P. And when you look at all these bars and all these letters on top, we see that the systems that apparently reduce total P loss and dissolved P loss was mostly the application of the annual maintenance rate in the spring, either banded or broadcast. See, this is the second and the third bars in the three graphs, and between the other systems, there wasn't much difference. This is very. I mean, we explain in the report that we wrote to the Nutrient Center. We haven't published this yet. This is something very particular happened in these 3 years. We got really rain and runoff early in the spring, late March or early April, before the spring treatments were applied. Okay, so then of course there was almost no runoff in some of the years, or very little, when we apply these treatments in the spring. But normally in Iowa, that's not what happened. You see, we have rainfall, intensive rainfall, early in the spring and late and during the planting period and after. So we need to take these results with a bit of grain of salt, because I wish we had another year, but we couldn't do it. So this also a complicated graph, but essentially shows. We also analyzed bioavailable P. There is a chart on the right. We see here this is the proportion of dissolved P of the total runoff P, and we see that both in dissolved and total dissolved P, you see that the total dissolved P is a bit higher than the dissolved reactive P. We see that there is essentially little effect, significant sometimes, but anywhere the proportion of dissolved P was from about 65 to 75%, and yes, it was a bit lower for the application in the spring with a planter, but I believe that's because of what I said before, that in these years were particular years with not much runoff after the fertilizer were applied in the spring, but yes, when they were applied in the fall. Okay, now we have the impact of soil conservation practices. There are all kind of many different conservation practices that I put in this slide. So I'm going to show you work that we have done over the years in some of those. Okay, one important thing about looking at the dissolved or the particular P loss is the tillage. And also we thought that was important, the P source. So this was a very large experiment that we conducted in Northwest Iowa from 2007 to 2012. So we have corn soybean rotations, 6 years, large plots under natural rainfall. We have each crop each year planted on adjacent plots, and we switch it over time to come up with a rotation. And then we have no-till or tillage. The tillage was a chisel plow disc in the fall for corn stalk, and spring disking only for soybean or also for the tillage treatment. And we try to maintain a soil test optimum to high, and we applied, as we explained before in this experiment, we applied the double rate for the rotation, okay, applied only before corn in the fall. Okay, then we had the treatment. The sources were broadcast, phosphorus fertilizer, broadcast, and with both tillage systems, and injected P-based liquid manure with both tillage systems, injected with a no-till and also with a chisel plow. We applied nitrogen fertilizer, so it wasn't limiting. I will just show the average across time. As we expected, the no-till greatly reduced the soil loss. This is soil loss, and I have on the left is the corn year, in the middle is soybean year, and the right, the rotation average. This is a very good result, and the others have found out there, in the United States, but this is the first that we have really documented 6 years that the losses of soil occur mainly in the corn year when it's planted on soybean residue. Okay, that's the chart on the left side. So look at the difference between the tillage, which is the gray bar, and the no-till, which is the dark bar. It's a major reduction. In the soybean year, also there is a reduction. That's the middle chart. But look at how low are the losses compared with the corn year, okay? And then, of course, we have the rotation average. So it is very important, Now, we know that. Soybean is great. We have to apply less nitrogen for the following corn, and that sometimes is very profitable. But from the perspective of soil losses, it is problematic. Now, here we show it's complicated again, but you can look at this, put stop, and look at this graph. See, on the right, I have the results for the broadcast fertilizer, okay? And in the right, I have the in bluish background, what happened with the injected swine manure. Essentially, there was almost no difference, okay? So I will not describe too much what happened with the fertilizer or with the liquid swine manure. It was about the same, everything. So if we look at the broadcast fertilizer charts, I have there, I don't have the rotation, but I have there the corn year first on the left, and then the soybean year to the right of that one. So the gray is the total P, the gray bars, and the black is the dissolved P. Okay, so we see here that the tillage effect on the phosphorus loss is very large for the total P, that includes the dissolved and the particulate P, and also for the dissolved P. But look at the difference between the no-till and tillage in terms of the proportion of dissolved P. We see with tillage we have about 20% of that is dissolved P, and with the no-till it's 54%, and that happened, in the soybean year and happened everywhere. This is something that is very important because it means that no-till is great, it's good, and we reduce total phosphorus loss. However, like this experiment shows, that we increase the proportion of dissolved P loss, and that P loss can be increased. For example, in the corn year, we have about 1 kilo per hectare of dissolved P loss, and with the no-till, we have almost 2. And with the manure on the right in the blue background, is a little bit lower, the difference, but still we have 38% with tillage and 59%. So no-till is good, but we reduce phosphorus loss, but we can increase the phosphorus loss, the dissolved phosphorus loss. Okay, we did many on-farm rainfall simulations from 2000 until actually 2018, more than 500 simulations all over Iowa using that contraption there. We use a methodology that was developed by the National Phosphorus Project that I participated in the early 2000s. So we were all over Iowa with my guys, Master Hack, Louis Thompson, Brett Allen, and others. So trying to see about the impact of salt SP, phosphorus, and manure source and other things on loss with runoff. So I'm not going to show all the results. I'm going to show some of the most important. This study was a nice one. We worked in 21 fields over 2 years. And the objective was to look at the effect of the manure source on the total and dissolved P loss when there is a rainfall immediately after application. This is very important that you remember. In all this case, We applied to the surface, no tillage, no incorporation, and we effected a runoff event within 24 hours of the application. That often happens out there. It's not so desirable, but it happens. So this is the extreme that will happen. So we have the runoff phosphorus loss, and I have, again, in gray, the total phosphorus loss, and in black, the dissolved P loss. Okay? So we have a control that we didn't apply anything. We have beef cattle manure spread by hand, poultry manure. We have different poultry manures here in the 25 fields. It was always solid. Liquid swine manure, and fertilizer. We use fertilizer as a kind of control just to see what happened. And then it's very clearly here that we applied the same rate, 100 pounds of P2O5, and we apply on soybean residue, okay? That the losses are very high with fertilizer. You apply fertilizer, and you get a runoff, intense rainfall event within 24 hours of the application, and the phosphorus goes. And almost 90% of that phosphorus was dissolved P. With liquid soy manure is the second ranking, but much lower, about half. Again, this was broadcast, this manure, okay, was not injected. And then poultry manure was less, and beef cattle manure was less. So definitely, this is the worst case scenario. There is a difference between the manures. Now, in the Iowa P index, we do not separate phosphorus sources because the P index is more than like a long-term tool. Okay, this is like a catastrophic thing. You see, what may happen if you do the wrong thing. You apply on the surface, and then it rains, within the 24 hours. And then the other interesting thing is that we see that the dissolved P, those blue numbers, are much lower with the beef and the poultry manure. They're about 30%. In liquid soy manure is about 50%, but it's with fertilizer. So really, people need to watch when they are going to apply fertilizer or manure that they are not going to get some high-intensity rain in the next couple of days. Now, the time to runoff, of course, may have some effect. So we conducted many experiments. This was with rainfall simulations in many fields because it's impossible to have a large study under natural rainfall to study, the impact of timing of application and things like that. So the time elapsing between the application and the runoff, okay, has a large impact, okay? And I will show some data, but essentially what happened, there is a big effect with pea fertilizer and liquid manure, okay? And then this effect of the timing of the runoff is lesser with solid poultry manure. We did not work with beef manure with that, but I assume that with solid manure is the same. So the issue with this is that we need to consider the probability of runoff causing rainfall along the year. In Iowa, normally, what our climate used to be at least, this is very high from late February to June, either snow melt or high-intensity rainfall in the spring, much less in the fall. You see, seldom there is runoff in the fall. And then another thing to consider is that the snow cover and snow melt runoff is very variable in Iowa, but it's much less than in eastern Corn Belt states or Minnesota. I say this because there is lots of research showing that the impact of snow melt runoff from both Minnesota, Wisconsin, Ohio, Ontario. But you need to remember, but in those states there is much more snow than in Iowa, and often they have really a thick cover. So when there is snow melt in the spring, usually the effects could be potentially much higher than in Iowa. So, okay, this was one study, one of the first we did, which is 2 fields. And we broadcast, again, 100 pounds of P2O5 to soybean residue, and we did it with and without incorporation, but at two different times. We did this in the fall. So the figure of the left, at the left, so we have the same that I showed before for the different sources. It was an event that we created within 24 hours of the application without incorporation, okay? It's no deal. So again, the gray is the total P, the black is the salt P, and then the blue numbers there is the proportion, the percent of the salt reactive P of the total P. So when we look at that graph, we see that it seems we're exactly the same as the previous slide. You see that the fertilizer is what really causes the major losses. Then comes liquid soy manure, a much lower poultry manure. And in fact, often this difference between the control, no phosphorus, and the manure was not statistically significant. It was really very low. And that's due, of course, because of the physical characteristics. It's not as much the proportion of the salt P in the manure. We tested that. It's mostly a physical characteristic in terms of the rain to remove that phosphorus from the manure that is applied over the surface. Okay, and then we see again, that with fertilizer we have 50% of the loss was with was the salt reactive P. Now, then in the center graph, we have the same rate, the same 24 hours runoff event, but with incorporation by light disking. So look at the incorporation, essentially reduced by half, less than half the phosphorus loss with the fertilizer, and reduce only a bit the losses with the liquid soy manure and poultry manure. Remember that the solid manure here was broadcast, okay, was not injected. So definitely when we are going to get an event shortly after the application, incorporation helps, but mainly with fertilizer, okay? On the right, we waited 10 days to create the event. It was different plots. So we applied all this, and then we waited 10 days, and then if there was natural rainfall, was very small, that produced no runoff within those 10 days, and then we created the runoff event. So if you look at the graphs in the center and in the right, you will see that actually a 10-day delay in the runoff event was even better than incorporating to reduce losses. Okay, so this, and we saw this in many trials. Really, just having that phosphorus sitting there on the soil surface reduces the losses of total and the salt P, because the fertilizer reacts with the soil. It's not necessarily fixed. There's not much fixation in Iowa. This is what happened. This is another study, which in this case is the same. In the top, we have the salt P loss in white background, and in the bottom with gray background. But in this case, it was a major study in two fields that we have several rates. Okay, we have like 1, 2, 3, 4 rates of liquid soy manure. Okay, again, applied broadcast. So all was the liquid soy manure broadcast, and either not incorporated or incorporated by disking. Okay, so if you look at the top and the left chart, you see the incorporation really reduces the dissolved P losses, and without incorporation is linear, very high. Okay, and the blue numbers again is the dissolved P. You can see that incorporation really cuts to a minimum the proportion of dissolved P in the runoff and the total losses. And below is the total P. The difference are less because we are measuring all the total P. Now look at the center two graphs, the white and the gray background. This was with a delay of 15 days. And then on the right, the two graphs are a 6-month event. So we waited. We did that in the fall, and then the other one we ran in the spring. And we when there was some kind of rain, either the farmer or us were there covering the plots. Okay, so there was snow, but not rainfall, in those plots, in those graphs to the right. So look at what happened. The same thing that happened in the previous study. When we wait 15 days to produce the runoff, there is essentially no difference between the incorporation and the non-incorporation, except for the high rate, and then when if we have little rain, actually not rain and no runoff for 6 months, there's no difference at all. So this happened in many situations. Okay, so it's very key, those that apply P on the surface, just waiting for a while can reduce surface a lot. And that's my problem with some policies in Ohio and around the Great Lakes, that they are essentially telling people not to apply P in any way to the surface, that they should do tillage if they're going to do that. Well, I don't know. As I said before, it rains more there in the fall than here, and there is much more snow. But I don't think that they ever studied this effect of how the runoff, the timing to the runoff event can affect that, And that's something that sometimes can be controlled. For example, application in the fall, the runoff is less likely in the fall in Iowa, okay, and probably Illinois, than it is in some of these other states. Okay, another study, this is a great study that Dr. Matt Helmers conducted in the Neil Smith Wildlife Refuge for several years, and they were looking at the impact of reconstructed prairie strips. That's buffer strip, grass buffer strips. It was a field study with the plots, quote, they're actually watersheds from about 1 to 3 acres in size. And the treatments were 0% buffer, okay? And this was no-till corn soybean rotation, okay? 10% of the area, but in the bottom of this in the slope, then 10% with buffers or 20%. Okay, they work a lot in with total P. They never measure dissolved P. So, in 2 years, 2013 and 14, I volunteered to do the analysis of dissolved P. Okay, so what this chart shows is the soil P loss on the left, okay, for 2013 and 2014. So, and I averaged all the 3 strips treatments because there was no difference between them from this perspective, okay? So, and you see that in 2013, there were large soil losses, and in 2014, much less. And the strips really cut the soil losses almost to 0. Those are the blue bars. On the right, we have concentration. Unfortunately, when I did this slide last year, I still haven't got the total P analysis that Helmets group was doing. So these are concentrations, okay? These are not losses. And then we see that here we have again total P in gray and the dissolved reactive P in black. And the blue is the proportion of dissolved P of the total P. So we see that there is a very, very, very large reduction of the total P concentration in both years. And in 2013, the proportion of dissolved P was very low, 1% for the crops and 6% on average for the strips, the percent of the runoff. However, in 2014, we have the reduction was relatively important too, but we see there that the dissolved P was 39% of the total P for the row crop and almost 60% with the strips. So definitely the strips reduce soil loss, reduce soil total P loss of particular P, but do not reduce the dissolved P in the runoff. So the other important practice that we need to discuss is the cover crops. It is well known that cover crops reduce soil losses, no doubt. There is the issue we have in Iowa with the cover crops. People look at effect of cover crops from all over the United States. We are in a particular region here in the north central region that the alternatives and the options that we have for cover crops are much less than the southern or eastern states. You see, we have the short season, all these issues. Now, Iowa and Minnesota research, lots of research has shown that the use of cover crop really reduces nitrate loss with subsurface drainage, essentially cuts anywhere from about 25 to 50%. Okay, it's important. But there was very little information about cover crops. At about the same time that we started one study, there was a study developed in Kansas, the only one I know, with natural rainfall that looked at cover crops and phosphorus loss, and created lots of hula with the result from the first year that the cover crop reduced the soil loss, but increased by a lot the dissolved P loss from there. So in our study, it was a 6-year study, and I was slow starting to release these numbers because I was fearful of 1-year data. So we started talking about this last year. So it was a 6-year study south of Ames. We used natural rainfall, all these things, H flumes, all that stuff. So there were many people involved over time. It was corn soybean rotation. Soil test P was high to very high, and we maintained that over time. We use a winter cereal rye cover crop each year. In the first year or two, it was drilled after harvest, but in the last 4 years, we overseeded before harvest. And there were 4 management systems with 3 replications. Watersheds were anywhere from 1.5 to 2 acres. No tillage, straight no tillage with the rye cover crop, tillage without the cover crop, and tillage with the cover crop. There were no phosphorus treatments here. So this is average of 5 years because there was no runoff in 2020, 0, it was a drought. So this is the runoff flow, is the amount of water loss on blue, and on the right is the soil loss. The only clear thing there is that with tillage we have much more flow, okay, and much more soil losses. Then there are some minor differences about between no-till and no-till with a cover crop. We see that the effect of the cover crop at reducing runoff as soil loss is really important with tillage. With tillage, the cover crop reduces the runoff flow to about half and reduces the soil loss to about 1/4, 1/3. However, in no-till, yes, the cover crop reduces the losses, but it's not as much, and that's probably because the effect of no-till, residue cover, and so forth. This is the averages, again, for the phosphorus loss, and I show in gray, again, the total P, and in blue, the dissolved reacted P, okay? And the blue numbers is the proportion of dissolved P of the total P. So if you look at the bars to the right, okay, tillage without cover crop or tillage with the cover crop, we see that something happened like in the soil loss, but not as much, you see. The cover crop reduced about half the total P losses. And in contrast to what happened in Kansas, it reduced the dissolved P loss. But the proportion is higher. Do you know that? You see, with tillage, no cover crop, the dissolved P is 36% of the total P, and with tillage with the cover crop is 54%. Okay. Now on the left we have the no-till. So the cover crop, of course, no-till reduces total P losses, the gray bars, but you see that the black bars are not that much different from the tillage to the right. And the effect of the cover crop is important, but is cuts by about half, no, to 3/4 the phosphorus loss, but it's less than with tillage. And the proportion of the runoff is 51% with no-till, straight no-till, and 58 with a no-tiller. So we were very happy with this result because this is in contrast with our result in Kansas. Now, Kansas is a different planet, different rainfall, different cover crops, different soils. So, but our study shows that with till as the cover crop, yes, it's a very good thing. With no till, yeah, it's good, but not that good. The other thing that we did across all these experiments is that this distinction, not all, most of them, looking at the difference between the total dissolved P and this dissolved reactive P that is commonly shown. So the dissolved reactive P are the gray bars with tillage in the left chart and with no till in the right. And you will see that on average, for fertilizer, for poultry and swine and OP, the total dissolved P is always a bit higher than the dissolved reactive P. So these dissolved reactive P measurements that everybody shows are underestimating the loss of dissolved P, which is the most active out there, okay? So it's not but much, see, but on average, it's like 10 to 20% higher than it says. So when they measure total P or dissolved reactive P, what they are measuring, they are assigning that that dissolved P that is not orthophosphate, but is active, they are assigning that to the particular P. So they are underestimating the impact of dissolved P loss. Okay, lastly, I want to show the effect of amendments. You see, there have been lots of talk in Iowa for the last years, mainly about gypsum. Applying high rate of gypsum is kind of like magic, it improves soil properties, yields, all that stuff. We work a lot with gypsum. It's a great sulfur source, low cost, but I'm going to show you some of the results that we got. In this first study, we compare DAP fertilizer with egg layers manure, and we mixed, alum or gypsum with the manure. And this was rainfall simulations. So in this slide, again, we use the timing of runoff. On the left, we show results for the 24-hour rainfall with no till. In the center, the 24-hour with tillage, and on the right, delay of 10 days with no till. The yellow is the total P, the green is the dissolved P in all the charts, and the blue numbers on top of the green bars is the proportion of dissolved P of the total P. And then we have the manure plus the alum, the manure plus the gypsum, the manure alone. So in a nutshell, what happened there is that the alum is aluminum sulfate. It really decreased dissolved P loss to 1/4 or something like that. It's really good. And we worked over 2 years with this study. And also reduced the proportion of dissolved P in runoff. And the gypsum did much less, and only with a no-till, okay? This result is important. It is kind of surprising because people are using alum in some other states to reduce P loss. And here, this was paid by the Iowa Egg Council. And they decided that it's too complicated to apply the alum with cage egg layers. So they may be easier for poultry, for turkeys, for broilers and turkeys, but not for egg layers. So they have not implemented that. I was telling them that they have a great chance of reducing the impact of poultry manure on water quality, but has not been implemented for some reason. We also did lots of experiments, with gypsum, with fertilizer. And I'm not showing any results because this is getting too long. And there was no effect at all. We did not, gypsum at several rates up to 1 ton per acre did not reduce the phosphorus loss with runoff, did not reduce the proportion of dissolved P with runoff. Essentially, only the alum did. So, in conclusion, there is higher dissolved P loss in high testing soils and higher with application of fertilizer and liquids and manure than with solid manures. There is higher dissolved P loss with increasing fertilizer and manure rates. Now, mainly with fertilizer and liquid manure, you saw that, applied to the soil surface. Mainly with runoff events shortly after the application. And then, as you say, be careful with spring applications because this is a period with very high intensity rainfall, very likely, and there is little time for that phosphorus to react with the soil. The probability that you spread phosphorus in the spring and you get a rain within 2-3 days is much higher, of course, if you do in the fall. The alum really dissolved P loss with mixed with poultry manure. Gypsum does much less, almost nothing. And it's important because the alum tends to acidify soils. But the poultry manure actually increase pH in soils, because of the calcium carbonate and all that stuff it has. So using the alum with the poultry manure application is not really a problem in terms of acidifying soils. So it could be implemented. Then we saw that no-till, cover crops, buffer strips reduce losses of soil and total P, especially particulate P, and almost always increase the proportion of dissolved P, but not necessarily the amount lost. You saw that in some studies, yes, the no-till increased the loss, in others did not, and the cover crop reduced the dissolved P loss, and the buffer strip increased the concentration of phosphorus runoff. But unfortunately, we did not have the loads. You see, we only have concentration, so we couldn't measure that. So, in summary, I believe that all these projects suggest that we have things that we can do, not just to reduce the total P loss, which is the most important thing in Iowa, but also the dissolved P loss. And with that, thank you very much. And I understand that you can send email or send questions to the organizers, and they will pass them to me. Thank you very much.